Hello, welcome to lecture 33 of the course. In the last class, we discussed normal mode splitting in the context of quantum optomechanics. In this lecture, we are going to discuss squeeze states of mechanical oscillator. Also, we are going to conclude the course. So, let us begin. In the last class, we have written down the linearized Hamiltonian in the absence of noise and damping as follows. That was minus h cross z a dagger b e to the power delta minus omega mt plus ab dagger e to the power minus I delta minus omega mt plus ab e to the power minus I delta plus omega mt plus a dagger b dagger e to the power I delta plus omega mt. And here let me remind you again that delta is the detuning parameter, which is defined as the cavity resonance frequency minus the laser frequency. Omega m is the mechanical resonance frequency. It's mechanical resonance frequency, and z is the optomechanical coupling parameter for the linearized Hamiltonian. Optomechanical coupling parameter. Okay, we discuss the situation when we have set delta is equal to plus omega m. That means the detuning parameter we set at resonance frequency of the mechanical oscillator. This actually refers to the case that delta is greater than 0, or in fact if you analyze it, because delta is equal to omega 0 minus omega L, so this is now equal to omega m. So you can clearly see that omega L is less than omega 0. Okay, and this is the situation or condition or regime called the red detuning. This regime we have discussed in the last class, and under rotating wave approximation in this regime we get our Hamiltonian as minus h cross z a dagger b plus ab dagger. Now as you know, a refers to the annihilation operator corresponding to the mechanical optical mode, and b refers to the annihilation operator corresponding to the mechanical mode. So these Hamiltonian physically state that one can transfer information from the optical mode to the mechanical mode and vice versa, subject to appropriate conditions. Now let us discuss the other case. Now let us take, or let us set the detuning parameter delta at minus omega m. So this will immediately tell you, because delta is equal to omega 0 minus omega L, and now this is equal to minus omega m. So you can clearly see that omega L, the laser frequency, is equal to omega m plus omega 0. So that means your laser frequency is greater than the resonance frequency of the cavity, and this is the regime of blue detuning. So this is the regime of blue detuning. Now we are going to analyze the Hamiltonian in this regime, and in this case the Hamiltonian, after removing the highly oscillating terms, that means I am talking about this Hamiltonian, if I put delta is equal to minus omega m, and then we can remove the highly oscillating term, then our Hamiltonian will take this form, that is minus h cross z ab plus a dagger b dagger. Okay, and this is what we get in the blue detuning regime, or when I said delta is equal to minus omega m. We are now going to analyze this Hamiltonian, and to do that, let us first write down the Heisenberg equation of motion for the mode A and B, and that is easy to do. We have done it several times in the course. So Heisenberg equation for the mode A, I h cross del A del t, that would be equal to A commutation AH. Actually, I am not putting the hat sign. Okay, then you will have here, this will give you minus h cross z b dagger, and from here therefore you can write dA dt is equal to Iz b dagger. And similarly you can get the other equation for the mode B, that would be dB dt would be equal to Iz a dagger. Now let us solve this coupled equation, and that is easy to do. What I will do, I can just take the help, because here I have b dagger, so from here I can write dB dagger dt is equal to minus Iz a, and you know how to uncouple this set of equations. So if I use this equation here, and from here I can get the equation d2a, the second order differential equation for A, that would be d2a dt2 is equal to z square a, and similarly I can get the other equation for B, that would be d2b dt2 is equal to z square b. So the solution, I can write a general solution for these two equations. The first equation will have the solution A of t is equal to, say, A cos hyperbolic zt plus B sin hyperbolic zt. I have to find out the constant A and B. We'll do that from initial conditions. Similarly for B of t, I can write C cos hyperbolic zt plus d sin hyperbolic zt. Alright, now let us take at t is equal to 0, say you can immediately get it, that would be A of 0 would be capital A and B of 0 would be capital C, and because we have dA dt is equal to Iz b dagger, this equation we have already got, and from this we can, now we know the we have already taken A, okay, dA dt if I take, so I will get Az sin hyperbolic zt plus Bz cos hyperbolic zt. These are very trivial algebra, as you can see. Then I have Iz b dagger, I also have B here, so A and B I have here. So B dagger would be, you will have C the dagger, or rather I'll say C is a complex quantity. Okay, let me write it like this, and I have cos hyperbolic zt, and then I have D complex conjugate of D, then sin hyperbolic zt. Okay, now at t is equal to 0, I have Bz is equal to Izc star, that would be equal to Iz, it would be B dagger 0, right? So from this equation, so therefore I have my constant B is equal to I B dagger 0. So I got my constant B, I got constant A and constant C, and you can find out in a similar way the constant D as well. So D would turn out to be I A dagger 0. So I got all my four constants. So therefore I can write the full solution as follows. So a of t would be equal to a of 0 cos hyperbolic zt plus I b dagger 0 sine hyperbolic zt, and b of t would be equal to b of 0 cos hyperbolic zt plus I a dagger 0 sine hyperbolic zt. These two equations lead us to a phenomena called two-mode squeezing. Two-mode squeezing. As the name suggests, two-mode squeezing, however, it does not mean that individual modes are getting squeezed. Rather, you will find that their relative coordinates or normal coordinates are getting squeezed or anti-squeezed. Two-mode squeezing is relatively a difficult concept, and let me explain it a little bit. In module 1, you may recall that in the case of single mode squeezing, we discussed this particular Hamiltonian, or a Hamiltonian of this form, who is had terms like, say, a square plus a dagger square, or maybe you have seen the Hamiltonian of this type where we wrote it as I h cross omega a square minus a dagger square. Both the Hamiltonians are equivalent because it has to be Hermitian, so either of the form is okay. So let us say we have this Hamiltonian. Then if you write down the Heisenberg equation of motion and solve it, you get an equation of motion. Then you can show that the solution is going to be a of t is equal to a of 0 cos hyperbolic r, where r is the squeezing parameter, a dagger 0 sine hyperbolic r. We discovered that this eventually gave squeezing in one quadrature of the annihilation operator A at the cost of amplification of the other quadrature. Now in the present case, the scenario is little bit different, because if you look at the solution here, as you can see from here, that unlike the single mode case, here the solutions involve both the oscillators. So you have here a of 0 is there, and as well as contribution from the other oscillator is also there. So individual modes are not getting squeezed or amplified, but something else is getting squeezed. In lecture 32, if you recall, we have written down the this annihilation operator A and B in terms of their quadrature as follows. We wrote A is equal to xa plus iya by divided by root 2, and B operator we wrote as xb plus iyb divided by root 2, such that with the condition that xa ya satisfy the commutation relation and xb yb satisfy this commutation relation, so that ultimately a dagger is equal to 1 and b dagger is equal to 1. From it we can write xa is equal to a plus a dagger by root 2, all these are operators, and xb is equal to b plus b dagger by root 2, while ya, quadrature ya is equal to I into a dagger minus a by root 2, and yb is equal to I into b dagger minus b by root 2. In terms of these xy quadratures of the two oscillators, we define the normal coordinates of the combined oscillator as follows. We have defined normal coordinate of the two oscillators, combined oscillators. X1 is equal to XA plus XB, and X2 is equal to YA plus YB. Okay, now it is a trivial exercise and very easy algebra you can do to show that the sum and difference of these two normal coordinates, say x1, the sum x1 of t plus x2 of t, or its difference x1 of t minus x2 of t, the sum and difference of these normal coordinates, they get the sum gets actually amplified. You can prove it very easily. X1 of 0 plus x2 of 0 e to the power zt. So the sum of the normal coordinates are getting amplified, while the difference in the normal coordinate, that is getting squeezed. So you will get this, you can prove this very trivially. Let me just give you an idea how to do that. You just need to do a bit of straightforward algebra, because you have x1 of t plus x2 of t. For example, you can write it as xa plus xb plus ya plus yb as per our definition, and then xa we can write in terms of, already we have this here, all this we can write in terms of their corresponding creation and annihilation operators. We just have to put it there. So you will get 1 by root 2 xa would be a of t plus a dagger of t, and xp is equal to b of t plus b dagger of t, ya divided by root 2, root 1 by divided by root 2, that anyway I am taking it out, and ya is equal to I into a dagger of t minus a of t, and yb is I b dagger of t minus b of t. Okay, now we know the solution a of t and b of t, and you can also get the corresponding a dagger of t and b dagger of t. You just need to put these solutions. What I am talking about is these solutions. You just have to put it there, do the bit of straightforward algebra, then you will be able to finally show that x1 of t plus x2 of t, this sum of the normal coordinates, as time goes on, these coordinates get amplified. It would be, you will get this, and for the other case the difference and would be equal to x1 of 0 minus x2 of 0 e to the power minus zt. And this is what we mean by two-mode squeezing when we are discussing squeezing of the combined oscillator, the optical oscillator and the mechanical oscillator. Let me point out some notable features of two-mode squeeze states quickly. Two-mode squeeze states is a superposition of states of the two oscillators. Here we are having the mechanical oscillator and the optical oscillator in optomechanics. Two-mode squeeze states refer to a highly correlated motion of the two oscillators. In fact, two-mode squeeze state, which we are not discussing in this course, are intricately related to the phenomenon of optomechanical entanglement. If we have two-mode squeezing, then we can also, there is a possibility that we will be able to find there is some kind of entanglement is happening between the optical as well as in the mechanical oscillator. Two-mode squeezing is its correlated state exhibit reduced quadrature noise, which is very useful for practical applications. For example, in optomechanics, squeezing of mechanical state is useful for ultra sensitive displacement detection, and this is particularly useful for gravitational wave detection, because as you know, the gravitational wave is a very weak signal, and if a gravitational wave has to perturb a movable oscillator, then we should not have any kind of other noise. There has to be other noise has to be very much low, so that we can get the influence of the gravitational wave, and in this case squeeze states are particularly useful. And also, if we want to study the validity of quantum mechanics in macroscopic domain, then generating squeeze state is useful and helpful. In fact, let me now talk about how squeeze state can be generated in the context of optomechanics. But before I do that, let me briefly introduce you to a useful mathematical tool which is often used to discuss non-classical states like squeeze states, and this mathematical tool is called Wigner function. Also, it is sometimes known as, or mostly it is known as, Wigner density. So I will just give a brief overview of what this quantity or this function is. The idea of Wigner density or Wigner function originated from this question: is it possible to define a probability distribution or probability density analogous to the classical probability density of classical statistical mechanics in quantum mechanics? So this is actually very desirable, because if we want to describe classical limit at high temperature, then this is going to be very useful, because you know that when we go to the very high temperature regime, then all the quantum mechanical principle are basically we may actually do away with the quantum mechanics, and we can use classical mechanics in those regimes. Now at first sight it appears to be hopeless idea, because you know that in classical mechanics the probability distribution is a function of the position and momentum, and in the so-called quantum mechanics, if we want to do that, let me just explain it this way. If we want to have, say, some probability distribution function, let me denote it by, say, p, and it is going to be a function of this x and, say, p, right? Because we are now quantum mechanics. But in quantum mechanics we know that it is not possible to measure position and momentum simultaneously. We cannot define them. So at first it appears to be a very hopeless idea. But Eugen Wigner, this gentleman who got Nobel Prize in Physics in 1963, he was a Hungarian physicist. In 1932, he came out with a technique which gives us quasi-probability distribution. This is not exactly the probability distribution that you get in classical physics, but it is quasi. Okay, I will explain what it means. This method turns out to be quite powerful, and now I am going to give you a brief idea only. Let us say we are given the wave function. Let us say we are given the wave function psi of x in position space, and we want to know the wave function in the momentum space. Let me denote it by, say, psi tilde of p. So what is this guy? And all of us know that this can be done mathematically by taking the Fourier transform of this wave function psi of x. So psi tilde of p would be equal to, so this is the Fourier transformation, and I'm sure all of you are familiar with this, e to the power minus I by s cross p of x psi of x. So if you take the Fourier transformation, mathematically speaking, then you will be able to get the momentum wave function from the position wave function, or if you take the inverse Fourier transform, you will get the other one. That means you will be able to get the given the momentum wave function, you will be able to get the position wave function. And the momentum probability density, if you ask, we can find that also. The momentum probability density would be simply the modulus of psi tilde p square. Let me get the expression for that using this particular expression here. So that would be 1 by 2 pi s cross. You have to take the complex conjugate, multiply psi tilde p with the complex conjugate, then it will give rise to a double integration. So let me define two different variables, x1 x2. So in one case I have to take the complex conjugate, so I will get I by h cross p x2 minus x1, and you will have psi of x1 psi star of x2. I think you can easily make it out. It's very easy. We are getting it from this particular expression. Now this could be written in a more simplified form by change of variables. So let me take, say, x1 is equal to x plus y by 2 and x2 is equal to x minus y by 2. That means I am going from this set of variables x1 x2 to a new set of variables x and y. And if I do that, you will see that Jacobian turns out to be, the determinant of the Jacobian of transformation is equal to 1. So therefore I can write this dx d2, this product would be simply the product of dx dy, and therefore I can now write my momentum probability density in the new variable as psi tilde p mod square is equal to 1 by 2 pi h cross, and you will have here dx dy, and I'm not writing both the integral. Okay, let me write double integral e to the power minus I by h cross. So x2 minus x1, you can see that this would be simply it will give you y, x2 minus y you will get. So you will have minus is cross py here, and here you have psi of x plus y by 2 and psi star x minus y by 2. Okay, this can be actually written, this can be written as psi tilde p mod square is equal to integration dx, and I now defined a new function w of x of p, and this is the so-called Wigner distribution function, and here I can read out that w of xp, this is the Wigner distribution function, is equal to 1 by 2 pi h cross dy e to the power minus I by h cross py psi x plus y by 2 psi star x minus y by 2. So this is what the Wigner distribution function is. In fact, given the Wigner distribution function, we can obtain the position probability distribution function as follows. If you are given the Wigner distribution function, the position probability distribution function would be simply the integral taken over the momentum space, that be dp w x of p. Okay, now if our quantum system is not a pure state, because you know that if we have a quantum system which is pure, we can define a wave function, but if our system is not a pure state, it is in a mixed state. That means it is in an incoherent classical mixture of different wave functions, each with different probability. Then this Wigner distribution function we can write as an ensemble average. So let me write it like this. You have W of xp is equal to 1 by 2 pi h cross dy e to the power minus I by h cross py. Now here I have to take the ensemble average because we have a coherent classical mixture of different wave functions, each with different probability. So we have to write it in this form. And if you recall that this I can further simplify, write it in a more familiar form. If you recall, we define our density matrix as, say, this is kth psi bra psi, and if I can write it in the position space, the density matrix as, say, x dash, I can write it in this representation. So I will have this, okay, and this guy is nothing but the wave function, position wave function, and this is the complex conjugate of the wave function, position wave function. So therefore, hence we can write the Wigner distribution function as follows: Wxp is equal to integration dy 2 pi h cross e to the power minus I h cross py rho x plus y by 2 x minus y by 2. Okay, now it is actually a straightforward mathematics to show that you can easily prove that this Wigner distribution function is normalized dx dp. This is just like your in classical statistical mechanics, the probability distribution function, you have dx dp is equal to 1, right? In classical statistical mechanics, the probability, total probability has to be equal to 1. Similar here, you are getting kind of analogous expression for the Wigner distribution function also, but there is a difference. The difference is that Wigner distribution function W of xp is always a real quantity, but it is always real, but it may become less than 0. That means it can become negative, implies though it is a real quantity, may become negative. So that means this is something which is completely different from the classical case, because in classical statistical physics, the probability distribution function, this p, this quantity is always a positive quantity. It can never be a negative quantity. Probability can never be negative, but the Wigner function can become negative. And whenever we have this function as negative, this Wigner distribution function as negative, no counterpart is found in classical physics, and those kind of states for which Wigner function becomes negative are called non-classical states. To give you an example, the so-called Fock state or the number state, for Fock state, the Wigner distribution function is found to be negative, and we don't have any classical counterpart of Fock state or the number state. I will not go into the details of the calculations, but let me show you some pictorial representation of quantum states using Wigner density. For example, the ground state of quantum harmonic oscillator. If I talk about the ground state of quantum harmonic oscillator, its Wigner distribution function can be represented this way. you have here say x-axis in the phase space and here the momentum axis, and the ground state of harmonic oscillator are Gaussian, and they have contour lines that are simply circles. So they are completely circles. Okay, and what about the coherent state? Coherent states of harmonic oscillator. As you know, the coherent states are displaced ground state of harmonic oscillator, so they are also easy to get. So these are Wigner distribution plot. So you have here P by M omega, because it is a displaced ground state. So coherent state, suppose it is getting displaced from the origin, and you have again this contour lines are circular, but only it is displaced. And now what about the squeeze states? Squeeze states are the states where one of the quadrasors are getting squeezed while the other one is getting amplified. So here you will have, say, this is x-axis and this is in P by M omega, the Wigner distribution function. Suppose originally we have this original state, this is the ground state of the harmonic oscillator, and now we squeeze it. If we squeeze it, say x quadrasor is getting squeezed while the P quadrasor is getting amplified. So then the Wigner distribution plot function, if you calculate it, you will get a plot of this type. Okay, here you see the x quadrasor is getting squeezed while the momentum quadrasor is getting amplified. Or you can also have a situation where you can have the momentum quadrasor getting squeezed and the x quadrasor is getting amplified. So these are what you will get. You can actually do the detailed calculations. Calculations are a little bit involved, but when you draw it this kind of a phase plot, this is very explanatory. Also you can have squeezed coherent state. You will see what I mean by squeezed coherent state is this. You have, say, these are your axes. Coherent state as such is, it is displaced ground state, and then you now squeeze it. Say you squeeze the x quadrasor, then your momentum quadrasor is getting amplified at the cost of squeezing of the x quadrasor. These are called squeezed coherent state. Okay, now let me give you a brief idea about how mechanical squeeze states could be generated in optomechanics. A good insight could be obtained if we discuss classical squeezing in classical mechanical harmonic oscillator. As you know that in classical mechanical oscillator, classical oscillator, the potential energy function for the usual harmonic oscillator is given as U is equal to half kx square, where k is the spring constant, and you know that k is equal to m into omega 0 square. Omega 0 is the natural frequency of the mechanical oscillator. Let us modulate the spring constant k of the oscillator. We do that by modulating the frequency by a small amount at twice the natural frequency. So if I modulate the spring constant, then I will do a time dependent modulation. So I will have this potential energy function as half k is the spring constant. I modulate by this amount, 1 plus epsilon, it's a small quantity, epsilon into sine twice omega 0 t, and we have then x square also. Here epsilon has to be a very small quantity. Okay, so if I introduce this kind of a frequency modulation or spring constant modulation, then you will find that we'll get kind of squeezing even in the classical context. Now if I use this potential energy function to write the equation of motion, so we have as mx double dot is equal to minus del u del x. This will give us the equation of motion for the modulated harmonic oscillator. That would be x double dot plus omega 0 square x is equal to minus omega 0 square x epsilon sine twice omega 0 t. Let me say this is equation number 1. We are going to use it. Now because epsilon is, this quantity is very small, we can guess a solution of this equation 1. So let us say x of t, the solution is of this type, where we have a cos omega 0 t plus b sine omega 0 t. Now if this modulation is not there, then a and b are going to be constant, but because we have modulated the harmonic oscillator, so these coefficients a and b, these are no longer constant, but they become some time dependent constant like this. But the time variation is taken to be very slow enough to neglect the second order time derivative of a and b. So we can neglect a double dot, as well as we can neglect b double dot. Now if we put this solution in equation 1 and also take these conditions into account, that means a and b variables are slowly varying in time, and after some straightforward algebra we can get these equations for the time evolution of a and b. A dot would be equal to plus epsilon omega 0 by 2a, and b dot would be equal to minus epsilon omega 0 by 2b, and these two equations has these obvious solutions. So a of t would be equal to a0 e to the power epsilon omega 0 t by 2, and b of t would be equal to b0 e to the power minus epsilon omega 0 t by 2. This implies that one quadrature component is increasing exponentially with time at the cost of the other one, because the other one is here b is decreasing exponentially in time. Now hopefully you can appreciate if I tell you that in optomechanics we can get mechanical squeeze states by exploiting the so-called spring effect, optical spring effect. And optical spring effect we have already studied in great details in one of the lecture classes. As you know, the optical spring effect simply means that the light field changes the spring constant of the mechanical oscillator, and we can change the spring constant as a function of time by changing the laser intensity. Now you can easily guess that if we can modulate the spring constant of the mechanical oscillator at twice its frequency, the particular mechanical mode could be squeezed. Now let me give you a quick quantum treatment of the whole idea, because now in addition to the usual Hamiltonian we have a part involving the modulated spring constant. Say that part is half m delta omega m square. This part is this particular piece is coming because of the modulation, and we have x square also. Now we can write this term would be proportional to the main terms that are let me just write them. We are modulating it at twice the frequency of the mechanical mode. Say that is cos twice omega mt. You can take sine also, doesn't matter. I am here taking cos, and then from x square part we have b plus b dagger whole square. This I can write as e to the power cos 2 omega mt, I can write as e to the power twice I omega mt plus e to the power minus twice I omega mt, and we have term b plus b Deger's square. Okay. Now we claim that only two terms are of significance, and these two terms are e to the power 2I omega mt b square and e to the power minus twice I omega mt b Dagger square. These two terms are important, and you can immediately see why it is so, because b varies as e to the power minus I omega mt. On the other hand, b Dagger varies as e to the power plus I omega mt, and other two terms are going to oscillate highly, and therefore we can neglect those two terms because of the so-called rotating wave approximation. Using the rotating wave approximation and going over to a rotating frame which is rotating with the frequency omega m, we can write our Hamiltonian by gathering all the other constant, putting it under this term h cross z. Let us say this is squeezing parameter, and we will have b Dagger's b square plus b Dagger square. This is the Hamiltonian which must be familiar to you, and this Hamiltonian is going to give us squeezing. I hope you get the main idea. Let me stop here for today. In this course, we have covered two primary platforms of quantum technology, namely the circuit quantum electrodynamics and cavity quantum optomechanics. In this context, we have learned all the essential fundamentals and also covered some mathematical techniques. I am sure this will help you to understand scientific literatures in the area, and some of you may even take up advanced studies or research. Thank you so much.